This is the beginning of Chapter 7, which involves applications of integration. In this video, we will talk about Section 7.1, which is the area of a region between two curves. And then Section 7.2 will be in the next video. So here we are interested in kind of analyzing how we would figure out the area between two curves. And you can see these pictures below. Remember, an integral essentially represents the area below a curve. So if you look at this first example here, this is showing us that we are interested in this area simply in between these two curves. And that area can be found by a subtraction problem. Now, if you look at this function, you can see that f is above g. And if I integrate the function f between a and b, I get this area here. Likewise, in this next illustration, you can see that g is here. If I integrate that, I get the area below g in between a and b. So what I can do is I can take this entire area, subtract out the area found by the integral of g of x, and that will give me the area between the curves. And that's what this statement is showing us. The area between function f and g is found by taking the upper function minus the lower function and integrating each of those. And that's what we're going to talk about as we move forward. So here is basically how you find the area of a region between two curves. And I think that illustration shown on the previous slide really hammers it in, but this will come up often and you will absolutely want to remember this. And this is assuming that f of x is above g of x or greater than. This is the interval of interest, so that is going to be our upper and lower limits. Now, basically, one thing that you want to be cautious of is if the function is always a top minus bottom type thing. Now, you might have something that looks like this, and you can easily see that the top function is always on top. So if you have a top minus bottom case, like this one, then everything is going to be in terms of x. That means your functions are in terms of x, and your limits of integration are in terms of x. There are cases, however, where the top minus bottom might change. Maybe instead you have something that looks like this. If you have something that looks like this, you can see that this linear function is on top, but then right here something changes, and now you have this function on top. If you have something like this, you have two choices. You can either use two integrals and have one integral that represents the red and another integral that represents the green. But that becomes pretty complicated, and instead, if you look, the function on the right is always on the right. So this could be a right minus left case. If you have a right minus left case, then everything can be in terms of y in your integral. So your functions in terms of y and your limits of integration are in terms of y. And then you will only have one integral rather than the two here. Now that may seem a little overwhelming, and I'm going to show you a few examples of each as we move forward. So take a moment and kind of digest this, and we'll move on to the next example. Here in example 1, we want to write a definite integral that represents the area of the region and then find that area. So here you're given two functions. y1 is the quadratic function and y2 is just the linear function. So you should be able to tell that this is y1 and then this line is y2. Now sometimes you'll only be given the functions, and if that's the case, you will want to sketch a picture of it or graph it in a calculator so that you can tell what the graph looks like. Now, if you're looking at this, at some point you're really going to want to tell if one function is always on top of another or if one function is always to the right of another. Now, if you look at this, the linear function is always above the quadratic function, and sometimes it's helpful to draw in those lines. Since the linear function is always above the other function, this is going to be a top minus bottom case, and it is always the top minus the bottom. If you have a top minus bottom case, everything is in terms of x. The function's in terms of x, and the limits of integration are in terms of x. So the top function is the linear function. So I know that this will be the top and this one will be the bottom. Now I want to show you real quick that you can do a right minus left case, but notice the quadratic is to the right. But then once you get here, then it's the quadratic minus the quadratic, which is still something you can do, but it gets a little more complicated. So that's why we want to do the top minus bottom. So if I want to find this shaded region, that is going to be the area between these two curves. So the area is equal to, we are going to integrate between an x value of -2 and 2. You can easily find these ordered pairs by finding the intersection of these. Remember, the intersection can be found by setting these equal to one another. So you can find the intersection by setting one function equal to the other and finding those x values. That's where those come from, if you can't tell on the graph. Now, since we have our limits of integration, we're going to take the top function, which in this case is 2x plus 5, minus the bottom function, which is x squared plus 2x plus 1. And don't forget the dx. So now this is something that should be straightforward. So what you're going to do is simplify the integrand, everything in here, and then integrate. So we'll distribute this, and we end up with the following. When we distribute, we'll have 2x plus 5 minus x squared plus, minus 2x minus 1. And we will continue to simplify. So the 2x's cancel out. So we end up with negative x squared plus 4. When we integrate this, we get negative 1/3 x cubed plus 4x. And we are going to evaluate this from -2 to 2. So remember, the fundamental theorem of calculus says we plug in the upper limit and then subtract out the lower limit. So when we do this, plugging in the upper limit, and then subtracting out what we get when we plug in the lower limit. Oops. All right, I'm going to kind of wave my hands a little bit, and you should be able to get this. This ends up being, I believe, 16/3 minus a negative 16/3. So remember, minus a negative becomes plus a positive. So when you add those, you get 32/3. And that will be the final answer here. So the area between the two curves is 32/3. Okay, in example 2, we are asked to sketch the region bounded by the graphs of the equations and then find the area. So in this particular case, we're given all these different functions, but not the graph. It is very, very helpful to draw a picture of the graph so that you can identify what type of case we are dealing with. Now, this here is a parabola that opens to the right. Since the y is squared, it opens to the right, and it's actually going to shift 1 unit to the right. So here's that parabola. This is just saying x is equal to 0, so we go through the x-axis at 0, which is really the y-axis. Then we have y equals -1, so that goes through the y-axis at -1. And then I have y equals 2, so that goes through the y-axis at 2. So the area that is bounded, or that we're interested in finding, is this region here. So we want to find this area. And it's important to notice that this area is not symmetrical because we're bounded by -1 and +2. So if I look at this, if I'm trying to identify if I should do a top minus bottom case versus a right minus left, notice how if we do top minus bottom, the bottom function changes. Here it's green minus green, and then here it's green minus purple. So we are not going to do a top minus bottom, and instead we are going to do a right minus left, because the quadratic function is always to the right of everything else. Now remember, if we are doing right minus left, everything needs to be in terms of y. That means the function, or the integrand, and the limits of integration. The limits of integration are simply the y values that sandwich this. So the y values of interest are from -1 to 2. So when I set up my integral, the area is equal to a y value of -1 to a y value of 2. And again, it is always the right minus left. So the right function is the quadratic, and it is already in terms of y, minus the left function, which is simply 0, because it is the y-axis. So when I set this up, it's actually a pretty simple integral to deal with here. Because this 0 goes away, I'm simply integrating y squared plus 1. So when I integrate this, I get 1/3 y cubed plus y, and we are going to evaluate that from -1 to 2. So applying the fundamental theorem of calculus, I'm going to plug in the upper limit first, which is 2. And then I'm going to plug in the lower limit, which is -1. And I'm not really going to take the time to simplify all of this for you. You should be able to do this. This grouping, I believe, becomes 14/3. This grouping is -4/3. Remember, this becomes plus a positive, giving you 18/3. 3 goes into 18 6 times. So this gives us an area of 6. Here in example 3, it's the same as the previous example, but now trig is involved. So we do want to sketch a picture of this. So hopefully you know how to sketch something like this. If not, graph it in your calculator. So here is pi over 2. This would be 3 pi over 2. Remember with sine of x, I always say that we start and end on the baseline. Halfway in between, we're on the baseline. 2 is the amplitude, so that's the height from the baseline to the maximum, and the height from the baseline to the minimum. So here is what the graph of 2 sine of x looks like, and of course we can mirror that on the other side. Remember that tangent of x is the same thing as sine of x over cosine of x. So whenever cosine of x equals 0, that's where the asymptotes occur. Cosine of x is equal to 0 at odd multiples of pi over 2. So these will be the asymptotes. So when we graph this, tangent is going to look something like this. Sorry, it shouldn't touch that. Okay, so we are interested in the interval from negative pi over 3 to pi over 3, which happens to be these guys here. And I know it's hard to tell by my illustration, but these are actually symmetrical regions. So we will also find that if I set these equal to one another, to find these intersections, if I were to set f of x equal to g of x, or 2 sine of x is equal to tangent of x, I will be able to identify where these where the intersections are, and that intersection is going to be my limits of integration. Okay, so that's what I'm going to do here, is I'm going to find my limits of integration by setting the two functions equal to one another. So I want you to recall that tangent of x is equal to sine of x. Sine of x over cosine of x. So I can move the cosine of x to the other side by multiplying. And then here, I can divide both sides by sine of x. So 2 cosine of x is equal to 1. If I divide both sides by 2, I get cosine of x is equal to 1/2. Now you should know when cosine of x is equal to 1/2. I'm not sure how your comfort level is with trig, but if you need some help with that, let me know. Cosine of x is equal to 1/2 when x is pi over 3 or negative pi over 3. So we have just verified that these are our intersection values for x. Now we need to figure out if we're going to do a top minus bottom or right minus left case. Here, the top function is always the sine function. So the top minus bottom case is probably the way to go. So since we're going to do top minus bottom, everything is in terms of x. So now we can do this one of two ways. We can integrate the entire function from here to here, or from negative pi over 3 to pi over 3, or we can use symmetry. So I'm going to show you how we can do this using symmetry. If I want to find the area of this, I can integrate from 0 to pi over 3, and that will give me the area of just this here. So if I do top minus bottom, that's 2 sine of x minus tangent of x. Now, this second region down here is the same as the region we are finding here. So I'm going to multiply this integral by 2 so that I can successfully find the area of both regions. Now, when I'm integrating this, your calculator can integrate this for you. You can do that, or you can do it by hand. Integrating tangent of x is sometimes something that students forget. You can look at the formula in your book or on the formula sheet I've given you. But I'm going to kind of wave my hands with this because really the integrating part is not part of this lesson. So this becomes 2 times, when I integrate this, I get negative 2 cosine of x minus the natural log of the absolute value of cosine of x. That is the antiderivative of tangent of x. And we're going to evaluate this from 0 to pi over 3. And again, you can plug all of this in. I'm going to kind of wave my hands because of time, really. So again, you're going to plug the upper limit in and then plug the lower limit in. And when all is said and done, you should end up with an area of 2 minus 2 natural log of a half. If you want the approximation, plug that into your calculator and you should get 0.614. Okay, this is the exact value, this is the approximation. Either answer is fine, just make sure you answer according to the instructions.